Operation IceBridge. You may know it from the beautiful photos that pop up in your feed. But did you know that IceBridge is the largest polar airborne survey of its kind? IceBridge was designed to study annual changes in the thickness of sea ice, glaciers, and ice sheets, as well as bridge the data gap between the ISAT and ISAT-2 polar observing satellites. Between 2009 and 2019, IceBridge flew over 1,000 scientific missions, gathering data that has redefined our understanding of the cryosphere. So let's take a look back at some of the mission milestones from over the years. One of the first steps to measure sea ice thickness is to get a handle on the amount of snow that accumulates on top of it. The IceBridge team pioneered the use of a snow radar instrument to gather the first widespread data set of snow thickness on top of both Arctic and Antarctic sea ice. Closer to land, the point at which a glacier begins to float is called a grounding line, and it's a very challenging place to measure ice thickness. Using two instruments, a radar sounder and a gravimeter, the IceBridge team was able to survey hundreds of these complex transition zones, enhancing scientists' understanding of the rapid changes in glacier behavior. In 2011, NASA scientists discovered a 19-mile-long crack across the Pine Island Glacier, one of the fastest retreating glaciers in Antarctica. The crack measured 260 feet wide and 195 feet deep when it was observed. Throughout the mission, IceBridge was able to map rifts in ice shelves prior to major calving events. And while these events are part of a natural cycle, IceBridge's observations helped scientists better record the changes in calving frequency and model how they may be related to a thinning ice shelf. The motion of the Antarctic ice sheet, the largest ice sheet in the world, is heavily influenced by the topography of the bedrock underneath. In 2013, the British Antarctic Survey used over 25 million measurements collected by IceBridge and other projects to develop a 3D map of Antarctica's bedrock topography. Called BedMap 2, it provided unprecedented detail of how the continent's bedrock shaped the flow of the ice sheet. Data collected by IceBridge enabled many discoveries in the Arctic as well. A team from the University of Bristol used IceBridge's radar data along with other data sets to uncover a 400-mile-long canyon buried under nearly 2 miles of ice. This hidden canyon is longer than any other known on Earth and provides a critical clue to modeling how melting ice is funneled into the Arctic Ocean. Using ice-penetrating radar data collected by IceBridge, scientists were able to build the first ever age map of the layers deep inside the Greenland ice sheet. For the first time, scientists could navigate the history of Greenland's ice layers, extending previously collected ice cores to better understand the ice sheet's history and help build models of its future. An international team of scientists used decades of NASA data to uncover a massive impact crater hiding beneath the Hiawatha Glacier in northwest Greenland. At roughly 1,000 feet deep and more than 19 miles wide, it is potentially one of the youngest large impact craters on Earth.
6, that's gonna 5, 4, 3, 2, 1. Mark on the overpass 0435 350.
ICE was bridged on April 8, 2019, with a direct underflight of the ISAT-2 satellite over Arctic sea ice. For the first time, both ISAT-2 and IceBridge would be taking the same elevation measurements over the same ice. These mirrored measurements were critical in validating the satellite's instruments and continue the legacy of IceBridge after the mission was completed. Over the course of its 11-year mission, IceBridge completed 1,056 scientific flights and provided a wellspring of data that fueled the publication of more than 660 papers and counting. The mission provided new insight into the processes driving the changes in the cryosphere, helping scientists better understand what we can expect in the future.
The human exploration of space is still in its infancy. The Apollo missions were just the first step in our goal to have astronauts working on the surface of worlds beyond our own. And as NASA plans its return of humans to the Moon and eventually onto Mars, a team of scientists have come together to test and build some of the tools our future explorers may use on these journeys. Based out of NASA's Goddard Space Flight Center in Greenbelt, Maryland, this group is called the Goddard Instrument Field Team, otherwise known as GIFT. The scientists in GIFT collect data on some of the most unique terrains on Earth, such as glaciers in Iceland, lava tubes in Hawaii, Mar craters in New Mexico, and the desert regions of Chile. The goal is to conduct field research in geologic settings that share similarities to locations on other planets, moons, and even asteroids. Scientists call these sites planetary analogs, as they help us learn how to interpret data from across the solar system, while also getting a better understanding of Earth. In these environments, GIFT researchers test both commercial and newly developed scientific equipment. These are portable devices that could be used by astronauts, or used aboard future rovers or other types of spacecraft. These field instruments are capable of multiple types of analysis, with some providing instantaneous feedback. The team uses devices that can observe and characterize the landscape around a user, as well as ones that analyze the chemical composition and physical properties of materials found at and below the surface. The team also works with instruments that measure aerosols in the atmosphere, magnetic fields, and solar radiation. No matter which field campaign they are on, the scientists in GIFT are selecting and using their instruments to answer high-priority science questions. And to more fully capture the essence of how humans would explore the surface of the Moon or Mars, GIFT members also simulate astronaut EVAs, or extravehicular activities, at the planetary analogs they study. Both former and current astronauts have accompanied GIFT on these simulations. Overall, the Goddard Instrument Field Team provides a unique resource to NASA and the external science community by combining the studies of planetary science, earth science, and hardware technology. All of the tests, experiments, and data collected provide a blueprint for the human exploration of other worlds. And that's a great gift for those taking the next giant leap.
I'm Ernie Wright. I work in the Scientific Visualization Studio. My producer David Ladd and I made this video for the 50th anniversary of Apollo 13. So Apollo 13 is pretty famously the moon mission where the oxygen tank explodes and the astronauts have to use the lunar module as a lifeboat. I'm a big fan of the Tom Hanks movie, but I wanted to do something that people hadn't seen before. Something that Lunar Reconnaissance Orbiter data uniquely allows us to do, to show what the crew saw as they flew around the far side of the moon. They arrive at the moon about a day after the explosion. They've been put on a free return trajectory that will sort of slingshot them around the moon and send them home. I found just enough data in the old Apollo documents to reconstruct their flight path. I put the virtual camera on that path, and I pointed it at the things they took pictures of, using the same lenses they had on board. So you see, like they saw, Tsaykovsky Crater and Mare Moscoviense, and the Lunar Highlands. By the way, a lot of the major features on the far side were named by the Soviet Union because they were the first to photograph it in 1959. I made almost 15 minutes of this stuff. David cut it together in a way that found the emotional beats of this part of the journey. The astronauts were behind the moon for almost half an hour, completely out of contact with the Earth. And you can just imagine what it felt like to see the Earth again, re-establish radio contact, and know that they were finally heading home. It took them almost 3 more days before they finally splashed down. The timing of the explosion was actually fortunate in a way. If it had happened during or after the moon landing, there wouldn't have been a lunar module to serve as a lifeboat. And if it was earlier, they might not have had enough power, air, and water to make it all the way back. Thanks for watching.
America has always been a fertile land. Grasslands and forests and farms, from sea to shining sea. The U.S. Department of Agriculture tracks how many acres and the annual yield for every crop produced. From the big ones like corn, wheat, soy, to regional crops like cotton, rice, citrus. They track every year using data from Landsat satellites and others, combined with data from surveys on the ground. Landsat satellites see detail at the human scale, about the size of a baseball diamond, and can image individual farm fields. The program started in 1997 with North Dakota as an experiment. Other states became interested, and the program grew. In 2008, Landsat data became free to use, and the USDA could afford to map 48 states. During the growing season, the data helps estimate crop yields, which helps farmers and traders set prices for the harvest. Thanks to Landsat's detailed view, the USDA tabulates stats crop by crop, county by county, and state by state. At the end of each year, the data set is released to the public, and it is a beautiful sight. The patchwork of corn in yellow and soybeans in green in the Midwest. The diversity of crops in California's Central Valley. The clusters of citrus in Florida and California and Texas. We can see changes in farming through the years. The easiest to see is crop rotation in the Midwest, cycling between corn and soybeans. In northern North Dakota, there is a shift from barley and wheat to soybeans and canola. And we see an increase in cotton fields, shown in red, in Texas and Oklahoma. Thanks to the free and open access to Landsat data, the U.S. Department of Agriculture is providing our farmers with accurate data and helping maintain our nation's food supply.
MAVEN is a spacecraft that's orbiting Mars. It's been there since 2014. MAVEN, in this case, is an acronym. It stands for Mars, Atmosphere, and Volatile Evolution. And this gives a clue as to what MAVEN's real goal is. It's to study the top of the atmosphere and how the gases in the top of the atmosphere might escape from Mars away to space.
So the atmosphere of Mars must have been a lot thicker about 4 billion years ago. And today it's very cold and dry. And MAVEN is meant to understand the atmosphere as it is today and how it has evolved into this current cold, dry state.
One of the things we're trying to understand with MAVEN is whether a magnetic field for a planet is important for regulating the climate or allowing the planet to keep an atmosphere. Earth has a global dynamo magnetic field. Mars does not, but Mars has an induced magnetosphere. It has an induced magnetic field.
The upper atmosphere of Mars is being ionized by solar radiation. And so the electrons are being stripped from the atoms in the atmosphere. When that happens, it turns into what we call a state of plasma. This plasma in the upper atmosphere is very conductive. It leads electric currents to flow through it. Electric currents, they shape the magnetic fields that are around them. And that's actually how we see them with MAVEN. We take magnetic field data and we map it around the planet, and from that, the currents emerge. We've known how the currents flow in the Earth's magnetosphere for decades, but we don't know how that works around Mars. We don't know how it influences the interaction with the solar wind, because it determines how energy is flowing into the atmosphere, how it's transferred from the solar wind into the system. And that's what we're trying to do with MAVEN. When you just look at the data as it comes down, you're just seeing a little squiggly line, essentially. You're seeing the magnetic field strength and its direction vary as the spacecraft is flying through different regions. And so what you have to do is you have to actually map it to the planet and to this interaction with the solar wind. And then it starts to emerge that you have a drape situation where the magnetic field of the solar wind encounters the planet and it starts to wrap around it. And the reason it wraps around the planet is those electric currents that we are seeing.
The magnetic field in the solar wind is straight lines. You can think of straight spaghetti noodles, and it's flowing towards the planet, and those spaghetti noodles wrap around this basketball-shaped planet. And that's indeed what we saw in the data, the magnetic field lines draping around Mars as a planet. One thing that wasn't so expected was the specific configuration of the electric currents that we derive from the magnetic field data. If Mars is a ball here, it's sort of this cup shape on the day side that loops back on itself, maybe something that looks like this. What wasn't so intuitive to me was the directions of those currents and the fact that it wraps continuously around to the night side, and it makes this marvelously complex current system on the night side as well.
This is the first time that we've been able to actually map out the currents, so we can see where the energy is being transferred. We can see what actually forms the underlying mechanisms creating these induced magnetospheres that are not just common here in the solar system, they're 50% of the planets that have them, of the terrestrial planets. And if you want to understand how the atmosphere of Mars and Venus, why they're so different from the Earth, and why they're so different from each other despite both being non-magnetized, we need to understand their induced magnetospheres first.
So knowing how these global current systems are configured teaches us about how charged particles near the planet are going to move, both charged particles in the solar wind and charged particles from the atmosphere itself that are in the process of escaping to space. So now we can understand better where those particles came from, how they move near Mars, and where they're going to go next. That in turn teaches us about atmospheric escape from the planet and the history of the atmosphere over time. How thick has it been? How much has been removed?
It's really satisfying to make someone else's ideas become a visual reality. My name is Bailee. I'm a motion graphics artist at NASA's Conceptual Image Lab. I start by asking a lot of questions, and then, I still use pencil and paper. I definitely doodle a lot and take notes during meetings, and then make some preliminary sketches. It's really tempting to start animating right away, but I think sketching those ideas out first really helps sort of lay the groundwork for the piece.
My name is Jonathan North. The first thing I do is try and get all the information about the project that I can. Ask all the questions. So for example, Dragonfly is going to Titan. I have to know how big Titan is, the surface, air quality, how it looks. So once I speak with the scientists and get all my information, I then go to a rough storyboard.
My name is Adriana Manrique. As we talk, I'll start sketching, even though if there's sketches that take 5 seconds less, just to get the ideas down They help me break down the big project. They help me troubleshoot things that otherwise I might not be able to even ask.
My name is Dongjay Christopher Kim. Sometimes there are projects that involve both 3D and 2D together, and I really do enjoy breaking that boundary. I think there was one piece I did with dark energy for W First, and it was a highly stylized piece, but it also used 3D models, but it was stylized in a way that it looks 2D, but I still had the freedom to move the spacecraft around in 3D.
My name is Jacquelyn DeMink. I tend to be generally the more hand-drawn style of 2D animation that usually looks more fun and cartoony. I enjoyed working on the Earth Expeditions project, the 5 different missions, because I not only got to do different style that I'd never worked with before, but also I got to learn about 5 different missions that NASA was currently doing.
My background, so I was born in South America in a country called Guyana. I was there until around 12 or so. Coming from Guyana, it really did influence my art style and artwork. I kind of tend to try to make everything a little brighter, a little more fun. Add a little something in there to add a little flair to the work.
Sometimes I'll get a lot of ideas, I guess, just from the natural world, like the way sunlight hits something, or maybe there's some flowers along a path that have a really interesting sort of color palette.
If I can get away with it, I like to use really bright, punchy colors. Especially if it's 2D, I like to have swooshing lines, things that are more sketchy almost, because I think it just gives the work a lot of energy, like a raw energy that's very appealing.
One of the biggest things is getting that believability of the work. These are digital images that we are creating to make you believe.
It makes science that would otherwise would be dry, it makes it very interesting. It even makes it very attractive.
I think science illustration just makes you very observant. Aside from all the techniques and stuff that you learn, it makes you look more closely at the world.
Have you ever tried to listen to your favorite radio station, only to find it garbled or replaced by a different station? Well, if so, you might have been the victim of something known as a sporadic E layer. There are concentrations of electrically charged gas called plasma in a region of space known as the ionosphere. They act kind of like mirrors in the sky and bounce radio transmissions over the horizon and interfere with your radio, kind of like 2 people trying to talk over each other. Even though we've known about these layers for over 80 years now, we still don't fully understand them because they occur at an altitude that is really difficult to explore. The air there is so thin that we can't fly an aircraft, but it's just thick enough that if we were to try to orbit a satellite, it would burn up in the atmosphere. So we've only ever been able to explore a handful. Well, one planet where the atmosphere is much thinner is the planet Mars, and one satellite that is currently exploring Mars is the MAVEN orbiter. One of the instruments on MAVEN is called STATIC. It's designed to measure plasma escaping from the ionosphere, this upper atmospheric layer of Mars. And in the data, scientists were seeing that when MAVEN would fly through a certain region of the atmosphere, poof, there was this big density enhancement of this plasma concentration. Scientists realized that they discovered the Martian equivalent of these layers. It's exciting because now we have a place that we can go to directly explore these layers with a satellite. MAVEN has encountered more of these layers at Mars than we've ever been able to explore here at Earth. At Earth, the layers are temporary and unpredictable, but at Mars they seem to be almost permanent and long-lived at predictable locations. Also, scientists found something that they didn't even know could exist. MAVEN discovered the opposite of a layer. They're calling it a rift, and it's where the sky has been pulled apart, and rather than a concentration of this plasma, there's a depletion. Many models said this actually couldn't happen, but yet they do exist, and we find them at Mars. This demonstrates how little we actually know, and how much there still is to discover. These layers are so common, they happen over our heads all the time. You yourself have probably detected one of these with your own radio, even if you weren't aware of it. And who would have thought that one of the best ways to explore them would be to send a spacecraft 300 million miles to the red planet?
This year, 5 new missions are taking off to investigate our home planet. From coast to coast, these missions will take a closer look at everything from sea level rise to snowstorms, all based right here in the United States. About 200 miles off the coast of San Francisco, the Submesoscale Ocean Dynamics Experiment, or S-MODE, will use measurements from a research vessel and 3 planes, a King Air, a Gulfstream, and a Twin Otter, to look at how swirling ocean eddies affect the movement of heat between the ocean and the atmosphere. Autonomous wave gliders and ocean gliders will dive below the surface of the water to get a full picture of the ocean and atmosphere. Together, the mission will collect data about temperature, salinity, and ocean velocity to get a better understanding of how small eddies affect the upper ocean. Traveling inland to the Midwest, the summer months can bring intense thunderstorms. Strong winds formed by these storms can overshoot the troposphere and reach higher in Earth's atmosphere, injecting pollutants into the stratosphere, which can affect the ozone layer. Using an ER-2 plane flying up to 70,000 feet, the dynamics and chemistry of the summer stratosphere, or DCOTS mission, will investigate how the pollutants reach the stratosphere and how their impact could change in the future. Farther south, the Mississippi River Delta is sinking as sea levels continue to rise globally. The Delta X mission, no acronyms here, will combine measurements from 2 planes, a King Air and a Gulfstream, with measurements taken on the ground and in the water to study how and where soil is naturally transported and deposited by water. This can help researchers better understand how the coastal regions will be affected by rising sea levels. On the east coast of the United States, the Aerosol Cloud Meteorology Interactions over the Western Atlantic Experiment, or ACTIVATE mission, will look at how clouds in the marine boundary layer, roughly the 2 kilometers above the ocean, affect the water cycle. These cloud systems cover large stretches of the ocean and are not well represented in climate models. ACTIVATE will use 2 planes, a Falcon and a King Air, to take measurements remotely and in situ, including releasing dropsondes through the clouds. Flying the same corridor, the investigation of microphysics and precipitation for Atlantic coast threatening snowstorms, or IMPACTS mission, will use measurements on the ground, scientific balloons, and 2 planes, the ER-2 and the P-3, to measure snowstorms at all altitudes. IMPACTS is looking closely at the intense bands of snow that form inside clouds to improve forecasting of snowstorms in the future. Stay tuned for more as these 5 missions take off.
I think one of the things that's really special about this visualization is that it's showing this new and really complex part of our model, which is atmospheric chemistry.
One of the issues, I think, with atmospheric chemistry is that it's so complicated and it changes so rapidly on a short scale. We're not necessarily able to observe it all the time, everywhere.
So that's where models come in. By merging models and satellite data, we get a much fuller picture of what's going on throughout the atmosphere. We can see gases that we couldn't see with satellites alone. We can see the parts of the atmospheric column that we really need to know, like the nose level contributions of pollutants that we need to communicate to policymakers to protect people's health.
So what we are seeing is a visualization of the composition of the atmosphere as it relates to air pollution. There are hundreds of chemicals that all contribute to those pollutants, and you can see in this visualization is really what the computer model does. Sort of like underneath, there are hundreds of chemicals. They all react with each other. It's a huge dating pool, and all of the chemicals date each other all the time.
So even though these chemicals, some of them are present only at these very dilute concentrations, they're actually quite important. So we have to really track all of these different molecules to be able to get at those pieces that people really need, the pieces of information that affect human health.
We rely on computer models to gain additional insights on where is it formed, where is it destroyed, what are the mechanisms and how it is formed, but also how can it be mitigated.
There's all this interesting stuff going on all around us that we're not necessarily aware of. And so this simulation is really just trying to illustrate what's going on with those gases, but by showing so many of them, illustrate how complex their interactions are and how many things are going on, even if we're not aware of them all the time. "10 years ago, we couldn't do anything like this." So this is really a revolutionary type of approach to be able to combine the satellite and the model. And the thing that impresses me the most about visualizations like this is just that we can do it. Just that with all of this complexity, all of these kinds of things being transported in the atmosphere, that this actually works. And when we compare it against observations, it actually looks really, really good in a lot of places. This is a really exciting new frontier for us.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It'll take us 3 years to make the rocket and only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the IceScat radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the north and south poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Kjell? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish, if we can.
This is IceScat. It's been very quiet, very difficult to launch.
No.
Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
Hi, I'm Joy.
And I'm Miles.
And we created the video about NASA's Visions 2 campaign in Svalbard.
It took 3 flights and a bus ride to get there, and when we finally arrived, it was around noon, but it was still pitch dark outside due to the 24-hour darkness. We wore headlamps everywhere we went, day or night.
The 24/7 darkness wasn't as jarring as I thought it would be, but I think that's because we also had a really hectic schedule. We'd wake up at 2:30 a.m. every day, I'd pack up all my filming gear, and then at 3 a.m. we'd head over to wherever we were filming that day.
Probably the hardest thing about covering this mission was that there were so many different things happening all at the same time. We really had to plan ahead to figure out where we were going to be when to capture it all.
One of the things I was most worried about was being stuck in the blockhouse during launch. It's this building right by the rocket, and when you're in there, you can't be outside during the launch. And you can only access that building by car with an escort, and you can only arrive and leave at certain times. But evidently, we didn't miss the launch.
And it was pretty much the best experience ever.
People have been hunting for sun-grazing comets for well over 100 years, but up to 1979, we only knew of less than a dozen. As of 2020, we have seen around 4,000 sun-grazers. Why did the number increase? The answer lies along the route most sun-grazers follow. In the late 1800s, Heinrich Kreutz observed that a few recent comets traveling near the Sun appeared to follow the same orbit. On this Kreutz sun-grazer path, as we've come to call it, it takes the comet several hundred years to complete one loop around the Sun. While there are other orbits of sun-grazers, Kreutz comets are the most common. All of the comets in this orbit came from a single comet that fell apart near the Sun thousands of years ago. As the comet moved closer to the Sun, the ice binding it together evaporated, breaking it into smaller pieces that the Sun's gravity pulled apart. Every time a comet comes around the Kreutz path, this can happen again, resulting in a new generation of comets. It might sound like this would clutter the solar system full of comets, but that's not the case. Most of the new comets are small enough that they become completely vaporized as they approach the Sun. There are more comets observed in the last few decades, not because there are more in the solar system, but because we have better ways to see them when they are close to the Sun. Spotting a sun-grazer from the ground is almost impossible because of the blinding sunlight. Now, spacecraft uniquely designed to look at the Sun can block the brightest sunlight, making the job a lot easier. Since the joint ESA-NASA mission SOHO launched in 1995, it has shown us thousands more comets than any tool before it. With SOHO, we can now see the smaller, fainter comets close to the Sun, just long enough to add them to our list of sun grazers before they vaporize. The spacecraft's data is available online, so now anyone can discover a comet. Roughly 95% of these comets have been found by amateur astronomers. SOHO isn't the only sun-observing spacecraft to have surprised us with beautiful images of comets. NASA's Solar Dynamics Observatory has spotted sun grazers too, though less frequently than SOHO. Now that we can observe comets better than ever, who knows? Maybe you will spot the next sun grazer.
In this clip, you will see 4 years covered in 100 seconds of data interplay, where over 500,000 of reported cases of Rift Valley fever affected humans and livestock. This data visualization gives you a peek into the scientific research efforts of Dr. Asaf Anyamba, who for over 20 years has been tracking diseases from space by combining hundreds of datasets from satellites and weather stations with disease reports and mosquito samples. This is what big science is all about, big data all around from the ground and from space, and science has proven that there is a cause and effect pattern between climate events and infectious disease outbreaks. The climate patterns of El Niño and La Niña, as measured in the Pacific Ocean near the equator, create weather anomalies whose ripple effects are felt with a 2 to 3 month delay in distant regions such as southern Africa. For example, the mild 2009 to 2010 El Niño caused an above-normal increase in rainfall and vegetation, which in turn triggered a large outbreak of mosquito-borne Rift Valley fever. We created this data visualization with Dr. Asaf Anyamba to showcase complex data associations and allow the viewers to track the key indicators over a period of time. In a sense, this visualization allows you, the viewer, to see with Dr. Anyamba's eyes and be guided to the conclusions by the data.
We are in a very remote environment. It's a harsh environment. You move slower, you're tired, your eyes hurt because it is so bright out there. You're cold, you can't remember the last time you were warm. And to, kind of make matters worse, you're digging giant holes in the snow. So you're working hard the whole time that all of these elements are just pounding on you.
The SNOWX project is really a multi-year campaign to test different instruments and techniques for observing snow characteristics in different regions and different snow types. So we collect measurements on the ground with different ground-based instruments and observing techniques. We use that to validate instruments on aircraft and in the air, and eventually, hopefully, get some instrument on a satellite.
One of the advantages of Grand Mesa is its elevation. We're at over 10,000 feet here, and so as you can see, the snow is not wet at all. And so we want to start by really proving the concept in dry snow. A lot of the remote sensing approaches are also challenged by complex topography, so really steep topography. And as you can see, where we're standing here, we're on the top of a mesa, which is relatively flat. This is the largest mesa in the world, and so it's a pretty unique spot to do this work.
Within the pits, we're looking at the vertical stratigraphy, so the layering of the snowpack and the different characteristics of those layers, temperature, density.
I'm operating the snow micro penetrometer, which is one instrument that they use in the pit crews to look at the hardness of the snow and to look at the microstructure.
The microstructure is a very important characteristic for these active passive microwave retrievals, so we wanted to get that in a lot of locations.
I've just done a radar survey in a particular way, and we use this type of sampling strategy. We're calling it a Heimstra spiral. It's a spiral pattern. I'm making 100 measurements per second as I drive the snowmobile, and that is a very similar measurement to what's happening on the aircraft.
SWISAR really stands for Snow Water Equivalent Synthetic Aperture Radar and Radiometer, and it's actually two instruments in one. It has an active radar and a passive radiometer. Basically, they both work on the microwave frequencies. And what they do is to penetrate the snowpack a little bit and give us the volume scattering information, then which we can relate to how much water is inside the snowpack.
Snow water equivalent is really the volume of water that's stored in the snowpack. For hydrologic applications, that's really the most important characteristic. We want to know how much is available to melt and where it's going to go, evaporate into our groundwater reservoirs, and how much is available.
Our climate's also changing, and snow is playing a really big role in that. And it's a big piece of the hydrologic cycle that's quite uncertain, and it's one of the pieces that we really see as a very high priority to get more quantitative, more accurate estimates for.
Snow is a really important part of our planet. It provides water, hydropower. It's a water source for agriculture and water supply.
When we have snow in our mountains, it's holding it and it's kind of like timing the melt in like a slow release versus just an onset of rain or a flood event.
As we build these records for longer time series, we would be able to tell how the snow accumulation is changing over a given area and how that might impact the agriculture in that area or how the people live in that area.
I'm really excited about the potential right now. I think there's a lot of excitement in the snow community. There's a lot of collaboration. I think we really are at a point where we can push the science forward and move towards a global snow product and a satellite mission, hopefully.
This is Bennu, a near-Earth asteroid, a remnant from the origins of the solar system and the target of NASA's OSIRIS-REx mission. When OSIRIS-REx arrived in December 2018, it brought Bennu into focus, confirming early radar images that suggested the asteroid was shaped like a spinning top. But the close-up images also brought a big surprise. Before OSIRIS-REx arrived, scientists had expected Bennu's surface to consist largely of fine-grained material, like a sandy beach. Sand heats up quickly during the day and cools off quickly at night. In contrast, solid objects like rocks and boulders heat up and cool down more slowly. Infrared telescope observations had shown that as Bennu rotates, its surface rapidly heats and cools, much like a sandy beach. But OSIRIS-REx was greeted by a rocky world littered with boulders, the size of cars, the size of houses, the size of football fields. This unexpected roughness confronted the mission with a major challenge. The main science goal of OSIRIS-REx is to briefly touch down on Bennu and grab a sample of fine-grained material for return to Earth. To protect the spacecraft, the original plan called for touchdown in a boulder-free zone with a diameter of at least 164 feet. But as it turns out, boulder-free sites of that size don't exist. Following arrival, mission planners began looking at safe zones that are just a few parking spaces wide, with enough loose material to provide a sample. In mid-2019, they identified 4 candidate sites and named them after birds that can be found in Egypt: osprey, kingfisher, nightingale, and sandpiper. Mission planners evaluated each site based on its safety to the spacecraft, the ease of getting to the site, the amount of sampleable material that it contains, and the science value of the material itself. After carefully evaluating these criteria, they chose Nightingale as the primary sample collection site and Osprey as the backup. Nightingale is located near Bennu's North Pole. It sits inside a small crater measuring 66 feet in diameter. Nightingale contains mostly fine-grained material and has multiple areas for sample collection. It is also the darkest of the candidate sites and has high color variation, suggesting a diverse mineralogy. Osprey is also located within a 66-foot wide crater, just north of Bennu's equatorial bulge, and may contain rock types from both the northern and southern hemispheres. Osprey has the strongest signal for carbon-rich materials of all 4 sites, and contains a dark patch at its center that is of high scientific interest to the mission. Now that the primary and backup sites have been chosen, OSIRIS-REx is performing additional reconnaissance flights to prepare for the sample collection event. Later in 2020, the spacecraft will descend to Bennu's surface, briefly touch down, and collect up to 4.5 pounds of loose material. After collection, OSIRIS-REx will carefully stow the sample and make the long journey back to Earth. In late 2023, it will return the sample, delivering pristine material from the origins of the solar system that will be studied on Earth for decades to come.
My land-covered career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything, because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I use satellite imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are made up of a series of pixels to show what covers the Earth. A pixel, or picture elements, is the smallest unit of a digital image. When combined with thousands of other pixels, a picture is formed. Each pixel color shown represents a land cover type. It's from these pixels where ground verification or ground truthing come into play. You see, depending on what satellite is taking images, a pixel can cover roughly an area of 30 to 500 meters squared. For imagery captured by Landsat, a pixel is 30 meters squared, or about the size of a baseball diamond. However, part of that pixel showing forest might actually be water, or shrubs. By taking land cover observations, citizen scientists can help answer these questions when it comes to land cover maps. So, why are these land cover observations so important? Why are they taken in the first place?
We also are looking at how these components are changing over time. So deforestation in the Amazon or across the world, how are cities expanding? A lot of different things to study, and really the view from space is the way that we do it here at NASA. We have big supercomputers that simulate the physics of the atmosphere and the land, the interaction between the Earth systems. It's important to have that, that land cover map. It sets certain parameters. Those models can actually be used to look at current day conditions and weather. So based on these current conditions, what might the Earth look like 50 or 100 years from now? There's an element of understanding, but then also being able to predict into the future, what that might be like, what these changes may mean for us.
Each point shown here represents a real-world measurement of environmental conditions. Scientists use computer models to fill in information where measurements may not exist. By verifying the satellite imagery and using the data for these models, scientists can predict changes in our environment more accurately. One of these scientists using land cover maps to track urbanization as part of her work is Dr. Amita Mehta of NASA's Goddard Space Flight Center.
So urbanization changes terrain as well as characteristics of the surface itself. And so impervious surface is what we look at when we are monitoring flooding. When there are, say, parking lots or cement and concrete surfaces, they increase. So previously, if it was a farmland or something which was not built, and if that is built now, that water previously that could go or percolate in the soil and in the ground now cannot go in, and it stays there. Monitoring helps you to plan for it. If you see land cover changing, even then you know that how water is going to flow in that region might change. If you have to send rescue out or you have to plan for relief activities, then if you know land cover, then you know where there might be help needed.
By using land cover maps and models that reflect changes over time, scientists can predict where flooding and other events may occur. With a changing climate, these predictions from models and land cover maps can help scientists better understand these changes and help communities prepare for them. But perhaps a more important reason as to why take land cover observations is you get to participate in a community of scientists, citizen scientists, and students.
So it's a very important component that the citizen science and students of the GLOBE program and GLOBE Observer can contribute to is by really giving us the information on the ground of what they're seeing around them and in front of them. And we hope over time as well how maybe some of these things are changing, because those would be very valuable for science.
I saw the value of having information before a hazard happens, because once that fire went through an area, we can never recreate that data. This is all important for us to share and put together because that's how we understand Earth as a system. All of these things end up affecting where we live, why we live where we do, and why we make some of the choices that we do.
To learn more about GLOBE Observer, Check out the website at observer.globe.gov and download the app to start taking your own observations today.
So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice. Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave. First, you should know exactly what a black hole is. A black hole is a physical object in space, just like everything else. It's made up of a tiny but massive point where gravity and density are infinite, a line beyond which everything, including light, can only fall into that tiny point, and sometimes some glowing stuff orbiting around it, and maybe some radiation. So basically, here is kinda bad, here is really bad, and here is safe. Also, black holes mostly come in two sizes. Don't ask me why, we still aren't sure. However, a black hole is also not a lot of things. It is not a hole, a cosmic vacuum cleaner, a portal to another dimension populated by unicorns and space potatoes, and absolutely not a good place to vacation. Okay, fine. I guess next you'll need to know how to find a black hole. Though technically black holes could just sneak up behind you, they likely won't. The nearest known one is 3,000 light years away anyway. However, if you were to go looking for one, there are a couple of good ways to find them. First, black holes tend to mess with their environment, so you can sometimes use interesting clues, such as a bunch of stuff orbiting what appears to be nothing. And second, as we mentioned before, there's often glowing stuff orbiting around them, caused by, well, when things get too close. So now that you've found a black hole and clearly aren't listening to me saying not to go, it's time for a few important safety considerations. First of all, the good news is that as long as you stay far away, black holes aren't all that bad. However, as you get closer, you need to keep a few things in mind. The radiation near the black hole can be extremely deadly. The chances of escape get slimmer the closer you get. And if you get close enough, you now have to worry about being stretched into a giant noodle and time getting really weird. So, unless you have great radiation shields, a faster-than-light spaceship, or you're completely indestructible, you should probably just stay away. Well, that pretty much sums up black holes, at least before things start getting really complicated. But before you go for real, please refer to the handy brochure in your spacesuit pocket, since there's quite a bit to remember. Now then, remember your tickets, enjoy your trip, and please, be careful.
A hurricane is Mother Nature's grandest but most ferocious weather machine.
A hurricane is two different things. If you're looking at it from above, from the satellite down, hurricane is a beautiful thing. It's a massive coil of clouds that is rotating, spinning like a top.
When I look at images of hurricanes, I go through so many emotions. As a scientist, as a meteorologist, I'm like, wow, this is fascinating. You know, look at this beautiful storm. But then the human side of me is saying, how can we make sure that people are evacuating, that people have somewhere to stay, that they have the money to feed their families once they leave their homes?
The hurricane on the ground, that's a completely different thing, because all of that rotation you really feel as incredibly severe winds. They can be up to 150 or more miles per hour. You can have up to 40 inches of rain. And the most deadly thing is that the updraft from the hurricane is actually pulling ocean swell up into it, and so it creates a storm surge up to 40 feet high.
And occasionally, when the storms hit at a little higher latitude, they can also spawn tornadoes in their fringe. So really the impacts are the wind, the storm surge, the heavy rainfall, and then occasionally severe weather that forms when they move inland.
I feel like I got a deeper appreciation for hurricanes when I moved to Galveston, Texas. That entire city, it's almost like the ghosts of the 1900 hurricane that are still there, because you see evidence of that storm, that particular famous storm that killed somewhere between 6,000 and 12,000 people. And so that is a very present, thing in the city, even to this day.
So that was a Category 4 storm that hit Galveston on September 8th. And there really was not a lot of information about what was happening in the Caribbean before this storm made landfall.
And the hurricane hit them totally unprepared, and thousands of people lost their lives, tremendous damage because it surprised everyone. With the onsets of satellites, that will never happen.
The first leap forward would have been being able to see the entire planet from space in the first place. Because prior to that, how would you know, for example, that a hurricane was coming? It would have been very difficult to know that where it was coming, where it was going, how bad it was going to be.
So that's one of the dramatic impacts, is satellite data, sort of like your eyes in the sky to make sure that Mother Nature never can surprise you.
You know, when I was a child, I loved playing with magnifying glasses because you can zoom in, you know, and see so many fine details. And that's what we can do with the satellites that we have now, particularly the GOES-R series. We're getting 60 times more data now than what we were in the previous series.
You know, the first satellites I worked, the GOES-I through M, which were great satellites, but taking a picture of the globe every 25 minutes, you know, the hurricanes would be like here, and then they're here, and then they're here. And it's not like you're losing track of them, but the difference between that and being able to see, you know, oh, it's swerving, it's curling, oh, it's, you know, it's dying. We take a full disk picture of the entire hemisphere in 5 minutes, but we can also look at smaller areas, and you can scan that once every 30 seconds. You get to see as the hurricane eye wall is forming, you can see that actually forming in real time. The Earth looks alive. It looks like a living thing.
So the polar orbiting satellites complement the geostationary. Since the geostationary, like 24,000 miles up, while they get great pictures, it's really hard to measure what is the state of the atmosphere from that distance. So the polar orbiting are basically flying a little over 500 miles up. And when you're at that altitude, you can sense what's in the atmosphere to a lot higher resolution. The JPSS satellite is really primary purpose is to take measurements of the temperature and moisture of the atmosphere to drive the weather forecast models.
Two things people always want to know about hurricanes are how strong is it and where's it going to hit. And microwave sounders can certainly help with both of those. The ability to see through clouds becomes really important. If you've ever seen a picture of a hurricane from space, mostly what you're seeing is clouds. And you can get a better weather forecast, a better prediction of how strong the hurricane is and where it's going to hit, which direction it's going to go, if you could see through those clouds and see the structure of the atmosphere. Maybe even the ocean conditions underneath that. And so microwave sensors allow you to do that kind of thing.
As you've seen, when they do the hurricane forecasting, there's usually a cone of uncertainty they put in the path. We don't know exactly where it's going, but for the next 3 days or 5 days or 7 days, here's the cone that it could go in. But you don't want to overwarn, right? You don't want to have the whole East Coast running inland 100 miles because of a hurricane, potential hurricane. You'd like that as precise as you can so that only the people who are really going to be affected have to do something. The improved sensors that we've been flying allow a better understanding of the core of that hurricane and allow the forecasters to better predict precisely where that hurricane is going to hit. And when they do that, then you can narrow and shrink that cone of uncertainty and give a better prediction.
We hope to continue to improve the ability to do track forecasting. That's gotten so much better over the past couple of decades. Our 5-day forecast is about as accurate as our 2-day forecast was only about 20 years ago.
And increasingly, people are listening to the forecasts that they get from meteorologists. They have increased confidence. They see the improvement in forecasts as it relates to hurricanes over the last couple of decades. And when a hurricane watch or hurricane warning goes into effect, people take notice and they take action. And that's really encouraging to see.
NASA's TESS mission has found its first Earth-sized world in its star's habitable zone. This means the planet, called TOI 700d, has the potential for liquid water on its surface. TESS stares at patches of sky for long stretches, recording light from thousands of stars. Some of these stars have planets that cross or transit in front of them. TESS sees these events as tiny, regular dimmings of the host stars. One star where TESS saw transits is TOI 700. It's a red dwarf about 40% the mass and size of our Sun and roughly half its temperature. One set of transits announced the presence of a planet close to the star, called TOI 700b. Another set revealed a second planet named TOI 700c a little farther out. The deeper, shorter transit means the planet is larger than the first, and the plane of its orbit is slightly tipped. A final set of transits showed TOI 700d orbiting even farther out. TESS observed this system for nearly 11 months and saw each planet transit multiple times. Scientists determined that the inner and outer planets are almost Earth-size and may be rocky. The middle world is more than twice as large and most likely made of gas. All three may be tidally locked, rotating just once each orbit, so the same side always faces the star. But most importantly, TOI 700d is within the star's habitable zone. Scientists wanted independent confirmation of TOI 700d, so they monitored its star with NASA's Spitzer Space Telescope. Spitzer saw a clear transit from the outer planet, affirming its existence and improving scientists' certainty of the planet's size. TOI 700d is one of only a few Earth-sized planets found in potential habitable zones. Others include discoveries by Kepler and several planets in the TRAPPIST-1 system. Because TOI 700 is bright and nearby, the planets are good candidates for precise mass measurements by ground-based telescopes. Future missions may also tell us if the worlds have atmospheres, but scientists need to know what kinds of signals to look for. Researchers at NASA's Goddard Space Flight Center created models of the planet to explore its potential conditions. One version is a water-covered world with an atmosphere similar to early Mars, but denser. Another looks like a completely dry version of today's Earth. Both models have vastly different surface temperatures. Light passing through their atmospheres creates distinct signals because different molecules are present. By simulating these data now, scientists can make predictions for real future observations and narrow the range of TOI 700d's possible conditions. We still have much to learn about the TOI 700 system, but thanks to TESS, Spitzer, and the work of many scientists, we're beginning to form a picture of its exciting new worlds.
The digital show NASA Explorers has a few different taglines. One of them is, "We follow intrepid explorers into the field." And that is true. And it's sometimes to places that are remote or can be hostile. We went to one location that I would not consider remote or hostile, but it was an adventure anyway. It was Boise, Idaho.
This mobile laboratory has been deployed for a very specific reason. The Shady Fire is burning nearby, and this team is gathering data that you can only get at night.
With a team of scientists who were tracking smoke, understanding the chemistry of smoke. It was really around the wildfire season, controlled burns, but just what smoke was doing to the air, what fires were doing to the land. We had the opportunity to follow this team, who you meet in one of the episodes, Bruce Anderson and his team out of Langley. We thought, it was 90 degrees that day. Like, we're just gonna sleep in the car and it'll be fine.
Hi, NASA Expeditions followers. I'm Katie. I've been doing a lot of the tweeting and the posting that you've been seeing. And here we have Lauren. Hi, guys. And driving our car, we have Ellen. Hello. she's not going to talk too much because she's driving. We are the communications team in the field with the FireX AQ mission this week, and we thought we'd give you a little behind-the-scenes peek at what it's like to be in the field.
It'll be warm enough, it'll be great, and we'll just follow them throughout the night as they take all these measurements. So, you know, almost instantly when the sun goes down, the temperature drops from around 90 or 95, somewhere in there, to 19 degrees.
We'll set out, drive up there, find a place to position the van, then start cranking up instruments.
And we're frozen. We're absolutely frozen in the car. And the thing is, the team is waking up throughout the night. You know, the scientists collecting data, emptying filters, and so we're trying to catch all these moments. It means that there's not a lot of sleep. It's really cold, but you have to stay somewhat awake so that you can catch the team working. I think what that experience allowed us to have is this real relationship with the scientists in the field, and especially Bruce Anderson. You know, there's a moment where we're talking to Bruce in the show, and he's talking about how why he does what he does, and I asked him this question that I tend to ask most people, and I think it's a really common question among producers, but we asked him, why do you do what you do? And the response he gave was one I probably won't ever forget, because it was so based in his life experience and a genuine desire to make a positive impact on the world.
For some of our scientists, understanding pollution has defined the course of their life's work.
I'm a physical chemist, but I'm also from what 60 Minutes called the most polluted city in America, Anniston, Alabama. When the opportunity came along to do this type of work, I really resonated with it.
He, of course, was interested in the actual science, but Bruce took this incredibly seriously. You know, he decided that he was going to pursue science, he was going to understand pollution all over the United States, all over the world, and be able to produce hard data that could help communities make better decisions about the way they wanted to live. We wouldn't have gotten that story from Bruce had we not spent this time with him in the field, if we hadn't gotten to know them as people. And I think being able to do NASA Explorers, it presents the opportunity to be humble about other people's stories and other people's motivations, to understand that they are multidimensional people who do the things they do because they're interested in science, but often there's a deeper reason and a deeper connection to the science they do. And it's our responsibility to tell them with dignity and respect. And we try and do that with our stories at NASA Explorers. So that's a little behind the scenes of how we got that story and how we got those shots.
Global temperatures are on the rise. As our climate changes, Earth is seeing more extreme and unusual weather. In 2019, the National Audubon Society reported that 2/3 of America's birds are threatened by climate change. That's 389 species in danger of extinction. Scientists at the University of Wisconsin-Madison are trying to figure out how temperature affects bird biodiversity across the country, which will help conservationists figure out where to prioritize their efforts. The team used data from Landsat's thermal sensor, called TESS, to map temperature across the United States. They also used a computer algorithm to map small-scale temperature differences. For example, a grove of trees in an open field. The algorithm compares the temperature variability in one area to those adjacent to it. The team then compared their temperature data to bird biodiversity across the country, focusing on the winter months and birds that don't migrate to find warmer temperatures. Turns out, large-bodied bird species tend to choose places with higher overall temperatures. But for small birds and climate-threatened species, having a habitat with variable temperatures seems to be more important. The researchers speculate that some birds may use pockets of warmer habitat, like a nest, a snow burrow, or a patch of dense tree cover, to wait out a cold spell or weather event. In the study, Temperature explained about a third of why some areas have more bird species than others, but that still leaves nearly 2/3 unaccounted for. To protect many bird species from extinction, scientists will have to find other factors affecting bird biodiversity.
The Hubble Space Telescope has had 5 servicing missions since its launch in 1990, from Servicing Mission 1 in 1993 to Servicing Mission 4 in 2009. Wait, what? 5 servicing missions, but the last one is called Servicing Mission 4? While it might seem strange at first, there's a reason for that, and that's because Servicing Mission 3 has a very interesting history. Originally scheduled for launch in mid-2000, Hubble's 3rd servicing mission was going to upgrade and refurbish the telescope just as the first 2 servicing missions had done before. But in quick succession, Hubble's all-important gyroscopes began to fail. So, why are Hubble's gyroscopes so important? Hubble Deputy Project Manager Jim Gilletick can explain.
So while we're turning Hubble, we need to know exactly which direction we're turning it. So we use a sensor known as a gyroscope, or a gyro. They use the conservation of angular momentum to tell us if Hubble is turning in which specific direction and how fast it's turning in that direction.
So essentially, without the gyroscopes, we have no way to know where Hubble is pointing, which, for a telescope, is kind of important. In 1999, Hubble needed at least 3 of its 6 gyroscopes to be running in order to do science. And with only 3 gyros still functioning, a Hubble emergency was declared, and Servicing Mission 3 was quickly split into 2 separate launches. SM-3A's main priority would be switching out all the gyroscopes with new and improved versions, while SM-3B was scheduled for a few years later and would work on the updates that Hubble still needed but weren't as urgent. Due to this timing change, the astronauts for SM-3A had less time to train for their important mission, but they went into overdrive and were ready in time for their launch date of October 14th, 1999. However, delays caused by final inspections and wiring repairs on the shuttle continued to push the launch date deeper and deeper into the end of the year. And then, as if things couldn't get any worse, in mid-November, a 4th gyroscope on Hubble failed. Hubble was put into safe mode, and all science came to a screeching halt. Thankfully, the Hubble team had already decided to split SM-3 into 2 missions months earlier. Otherwise, Hubble would have been totally silent until the originally planned mid-2000 mission. So, after a few more delays due to more inspections, rewiring, engine replacements, and bad weather, the crew of SM-3A, sitting in the cockpit of the Space Shuttle Discovery, was ready to launch. The 8-day mission had 3 spacewalks planned. The first was the all-important gyro switch-out. There were a few minor problems that came up during the 8-hour, 15-minute-long spacewalk, but by the end of the day, Hubble's gyro troubles were over. The next 2 days had their own spacewalks, updating Hubble with a more advanced computer, adding a new fine guidance sensor, installing a new solid-state digital recorder, and replacing Hubble's old outer insulation with new panels in order to protect Hubble's scientific equipment from getting too hot or too cold. When all the work was finished, Hubble was released back into orbit on Christmas Day, and as the crew of Discovery landed at Kennedy Space Center, it became clear that this mission was a resounding success. Servicing Mission 3B would also be a success later in March of 2002, followed by the fifth and final flight, servicing Mission 4 in May of 2009. Thanks to everyone involved with servicing Mission 3A, Hubble was able to quickly get back on schedule with its groundbreaking science and continue forward with its mission of uncovering the mysteries of the universe.